Okay, let's look at what happens with surds when there's some multiplication going on. We've got the square root of 4 times 9 here. Now I can work that out directly because I know that 4 times 9 is 36, so that must be the square root of 36. And I know that 6 times itself is 36, so the square root of 36 must be 6. Okay, starting with this other one, I can do the square root of 4. 2 times 2 is 4, so that's 2. 3 times 3 is 9, so the square root of 9 is 3. And 2 times 3 once again is 6. So these two expressions, although they looked a little bit different, turn out to equal the same thing. And I might start thinking that this will work for any two numbers, but I mustn't jump to conclusions. Just because things look like they might work, we mustn't assume they do. And indeed, if I did this with addition, if I did 4 plus 9 inside the square root, then I'd get the square root of 13. And that certainly isn't the same answer as I would get from the square root of 4 plus the square root of 9, because that would be, square root of 4 is 2 again, square root of 9 is still 3, and 2 plus 3 is 5. And 5 is certainly not the same thing as the square root of 13. So it looks like there's something about multiplication that maybe means that surds work this way. I can multiply the two separate square roots and get the same answer as multiplying before I take the square root. But this needs proof. So in order to prove it, I'm going to start with the square root of a times the square root of b. If I'm right that these two things are always the same, then this should be the same thing as the square root of a times b. Well, let's test it. Let's see if it is. So let's try squaring this. Okay, so if I take the square root of a times the square root of b and just see what happens if I square it, then that means I do it times itself. So I've got the square root of a times the square root of b, and then the same thing again being multiplied. But of course, in a multiplication I can change the order of the terms. So I can put the square root of a times the square root of a times the square root of b times the square root of b, same four things, just in a different order. And of course the square root of a times itself, its job is to equal a. So I've got a for that part of the calculation, and this part of the calculation, the square root of b times itself, is b. So the answer is a times b. So when I take this object here and I square it, I get the answer a times b, or just ab for short. So this is the thing that when I square it, I get ab. So therefore, the square root of a times the square root of b, because it's the thing that I have to square in order to make ab, the square root of a times the square root of b is the square root of ab. And that confirms the pattern that I noticed when I used 4s and 9s. Okay. Similarly, if I take the square root of a over the square root of b, that's an a, not a 9, and I try squaring that, so if I square this fraction, then I get the square root of a over the square root of b times itself times the square root of a over the square root of b. And when I multiply the tops and multiply the bottoms, that's how you multiply fractions, on the top, square root of a times itself is just a. And on the bottom, the square root of b times itself is the square root of b. Not the square root of b, it's b. So this thing here, when you square it, you get a over b. So it must be true that the square root of a over the square root of b, I've just seen it's the thing that I need to square to get the answer of a over b, sorry, so it must be the square root of a over b. So we've derived two results here which we can apply to combining square roots with multiplications and divisions. Okay, but bear in mind that not all things work that way. Remember, we tried doing similar things with additions. It doesn't work.